Welcome to this web lecture on the maximum flow problem. So let's just assume we're TUI Airlines and we're operating a network of direct flights in Europe, and within this network we're allowing passengers to change over between flights. So for instance, if I want to go from Rome, so FCO, to Brussels, I can transfer in Zurich in between. So now TUI Airlines is having a little bit of a problem. They used to have a direct flight from Rome to Amsterdam, but this was cancelled today. And due to that, we have to reassign passengers to different flights. So we can ask multiple different questions in this context. For instance, we can ask how many passengers can we reassign the most? How can we reassign the passengers from cancelled flights such that we minimize costs? Which passenger shall sit on which seats? And we could potentially also ask the question, does it help to send additional flights? Today we're going to look into the first question. So we're going to look into how many passengers we can reassign the most. And for that we're going to use the maximum flow problem. So what we want to do is we want to send as many items as possible from a source to a sink. So in the context of TUI Airlines, this means sending as many people as possible from Rome to Amsterdam through this network. So now we want to model this as a mathematical model. So what we're doing is we're looking into the recipe for formulations, which tells us, okay, first identify the sets, then identify the parameters, identify the decision variables, formulate the constraints, and formulate the objective function. So which sets are we having in this problem? Quite clearly, we somehow have to model the airports. So we have an airport set which we denote by V. Secondly, we have to identify the parameters. Quite clearly, the parameter that we're going to need is an arc capacity. So we need to know how many people can travel, for instance, from Rome to Toulouse, and we obviously don't want to exceed that. Third, we want to introduce the decision variables. So which decision variable do we very clearly need? We very clearly need to know how many people are traveling on an arc, and we denote this by xij. So the next step that we have to do is we have to define the constraints. So the first constraint that we obviously have to adhere to is arc capacity. So we don't want to send 7 people from Rome to Toulouse if we only have 6 seats on this flight. Okay, so what you're seeing here is the optimal flow, or a part of the optimal flow. So we have 2 people going from Rome to Toulouse, which then continue to Zurich. We have 10 people that directly go from Rome to Zurich. And then we have 12 people that go from Zurich to Brussels, which is no longer on this slide. So let's just say we would accidentally set our flow to 0 from Rome to Toulouse and from Toulouse to Zurich. So like this. What now happens is that we have 10 passengers. They go from Rome to Zurich. But then, all of a sudden, to still satisfy the flow that we are currently setting from Zurich to Brussels, we actually have to somehow find 2 additional people. Or vice versa. If we now only have a flow of 10 from Zurich to Brussels, then what happens is that we have 12 people that start in Rome. They also travel to Zurich, but then all of a sudden we leave 2 people here, which is obviously nothing that we want. So what we need is so-called flow balance or flow conservation constraints, which means that we leave no passenger stranded. And this means that whatever comes in also has to go out. So the next thing that we have to ensure if we look into this network is that we don't have any weird flows. So if you look into this network, let's just say we have 1 additional arc from Zurich to Rome, which has a capacity of 100. And now what we can do is we can send people along this arc. So we can send 20 people because that is the remaining capacity from Toulouse to Zurich. And all of a sudden, we have a lot more passengers, but it doesn't help these passengers because they just end up back in Rome. They wanted to go to Amsterdam, not to Rome. So we also have to ensure that we do not have any cycles. So we don't have any passengers that enter Rome again. And the last constraint that we have to consider is the non-negativity of the decision variables. So obviously we don't want to have -5 passengers flying from Brussels to Amsterdam. That would not make a lot of sense. The last step that we're doing is we're formulating the objective function. And our objective function is to formulate the flow. So let's just say this is what we want to do. We want to maximize the total flow that goes through this network. The problem is this is wrong. And as a homework, you can show why this is wrong, and we're going to discuss this in class. The correct objective function is maximizing the number of people that leave Rome or that enter Amsterdam. And yeah, please show as a part of your homework on why this is the case. So what I want you to take away from this web lecture is, first and foremost, the problem formulation of the maximum flow problem. Secondly, the wrong objective. And this is also part of your homework. Please correct this objective. And what we're going to do in 2 consecutive videos is, first of all, we're going to look into an algorithm for the maximum flow problem, the so-called Ford-Fulkerson algorithm. And lastly, we're going to look into the assignment problem, which actually also boils down to a maximum flow problem.